Good morning, everyone. So it's time to learn section 11.8. It's our first day of the second half of chapter 11. And we're going to start by learning something called a power series. And then from the power series, we're going to learn how to find radius and interval of convergence. So let's begin. So a power series is a series where when you list out all the terms, it looks a lot like a polynomial. So you end up with like a coefficient times x to a power. So one of the things you'll notice that's different about a power series from all the series that you've been studying in the first half of chapter 11 is the fact that you've got this x right here. So that x is what takes that series and helps us kind of turn it into what eventually will become a function. But right now we're just going to study it as a series. So x is a variable. The c sub n's, those are constants. Those end up being the coefficients of the series when you plug in all the different values of n. And just so you know, we're going to learn, they don't have to look exactly like this. We can actually have the coefficient times x minus a constant and have it still be called a power series, which we'll learn on the next slide. So, I guess the next slide. So anyway, so the sum of the series of a function, so you've got that. So if f of x, some function, is equal to the series, the thing about it without adding that x variable in is the series without the x, when we just had numbers, the series either converged or it diverged, and that was it. Now with these x variables in, a series might converge for some values of x, and it might diverge for other values of x. So for example, if we have the series x to the n right here, and if you list out the terms, you get 1 plus x squared, and so forth. Well, if your x is a half, like this guy right here, well, then you have a half to the n, which is a nice geometric series. The common ratio is less than 1, so you end up with a convergent series. But if you have an x value that's bigger than 1, like 2, you have a non-converging or diverging geometric series. So it depends on what value we pick for x, whether or not this series converges or diverges. And that's kind of what we're going to study today, is how to find those values of x that will cause the series to converge or diverge. So this is what I was talking about 2 slides ago. So you can also have a power series where instead of just an x, you have this x minus a, and a is called the center. It's called the center. And I'm going to show you next week what that really means. There's very nice visuals that I can show you to show you what does a power series mean when it's centered at A. I'm going to show you that next week. So anyway, just know for now that think of A as the center, and then values are kind of coming out from A. But apart from that, you don't have to worry about it too much right now. Oh, little note, a power series will always converge at the center. So whatever that center happens to be, notice if it's just x to the n, you still have a center, it's just 0, right? Now, why does the power series converge whenever x equals a? Because if x is equal to the center, then all of these terms going forward, you get a minus a, which is 0. Goodbye, goodbye, goodbye. And all you're left with is this little constant right there. So of course the series converges, because remember the series is the sum of all the terms, and as long as that sum of all of the terms equals a finite number, the series converges. In this case, the sum of all the terms would just be that first coefficient, and therefore it would converge. Okay, so let's go ahead and do a problem that you might see tonight, just so you kind of learn what we're doing here. So for what values of x is the series n factorial times x to the n convergent? Whenever we're determining convergence, we're always going to use the ratio test. every single time we're doing power series, we're going to use the ratio test. So the good news here is you don't have to sit there and try to figure out what test to use. You're always going to use the ratio test for power series. So let's go ahead and do our limit as n approaches infinity of the n plus 1th term over the nth term. All right, so n plus 1 factorial, that's the same as n plus 1 times n factorial. X to the n plus 1, that's the same as x to the n times x to the first. And on the bottom, we still have n factorial x to the n. So what ends up happening is the n factorials cancel, the x's to the n's cancel, and we're left with the limit as n approaches infinity of n plus 1 times x. Remember, x is a constant. N is going to, well, when we're talking about this limit, x is a constant. So in terms of the limit, n is our variable. N is approaching infinity. Infinity times a constant is infinity. So it looks like this series diverges for every single possible value of x. However, every single power series must at least converge at the center. So the only x value where the series converges, so I'm going to write our series, make that bigger, converges at x equals 0 only, because our center is 0. So if you get a limit that where it looks like every single value diverges, like the boy, is that bigger than 1, right? Then you still are going to converge at a minimum at the center. Okay, so a couple new things. So first, a power series, there's 3 possibilities for convergence. Either you only converge at the center, or you converge for every single possible value of x, or you converge on some interval of x. So the interval of x where the power series converges, that's called the interval of convergence. And even if it's just a point, you can still write that as an interval. It would just be the same point to itself. But yes, so the interval where the power series converges is called the interval of convergence. And I'll show you in a minute, the radius of convergence is how far away from the center the power series converges. So you kind of have that x minus center in the middle, and that has to be less than some radius. And it's actually easier to find than you might think. So what we're going to do in the next few problems is we're going to learn how to find the radius and the interval of convergence. And don't worry if you're a little confused on what the heck do these mean. I promise I will show you next week a little bit deeper and a little more visually what radius and interval actually mean. Oh, last little tidbit. When you do the ratio test, your interval will always be an open interval. The ratio test does not check the endpoints. So when you do the ratio test, once you've completed it, you still have to test each of the endpoints of the interval to see whether or not your interval is going to be closed or open. So we'll show you that when we do the next example. Okay, so we're going to find the radius and interval of convergence for the sum 3 times x minus 2 to the n. So first thing I'm going to do is set up my ratio test. And I'm going to go ahead and write, let's see, 3 times x minus 2 to the n plus 1 over 3 times x minus 2 to the n. Okay, so hopefully you'll see like the 3's just cancel. That's easy. So let's go ahead and just clean this up. So x minus 2 to the n plus 1, I'm hoping you're kind of getting used to that. That's x minus 2 to the n times x minus 2. As a matter of fact, I'll write that out. This right here, that's x minus 2 to the n times x minus 2 to the first. So what happens is the x minus 2 to the n's cancel. We're just left with x minus 2. There are no n's in this expression. So this limit, it is what it is, right? As n approaches infinity, since there's no n's, this limit, it works, right? It's so anyway, so what do we do with this? Well, so now we're kind of thinking about what on earth do those values of x have to be? Well, we know that the series converges if our limit is less than 1. So what we end up with is absolute value x minus 2 is less than 1. And if you look back on this page, the radius of convergence, if you have something set up where you have absolute x minus a is less than r, whatever this number is, that's your radius. So our radius for this problem, so our r is 1. Now to find the interval of convergence, let's remember how we deal with an absolute value inequality. If you have absolute x minus 2 is less than 1, that means either x minus 2 is less than 1 or x minus 2 is greater than negative 1. We can write this as a compound inequality. So you can write negative 1 is less than x minus 2, which is less than 1. To solve this inequality, you're going to add 2 to all three sides. So if I add 2 to all three sides, I'm going to write plus 2, plus 2, plus 2. So I get 1 is less than x, which is less than 3. And therefore my interval of you know what? I can't write it yet. Hang on, we got to test the endpoints. That's my open interval of convergence is from 1 to 3. Now we got to test the endpoints. So we have to test at x equals 1 and x equals 3. So how do we test these endpoints? You're going to go back to your original series and replace the x with a 1 and then replace the x with a 3. So our series is 3 times x minus 2 to the n. So if I do the sum, I think it was 1. 3 times 1 minus 2 to the n. So what I get here, so I get 3 times negative 1 to the n. So this guy, if I do a limit as n approaches infinity of 3 times negative 1 to the n, this limit does not exist. And therefore, this series diverges by nth term test. All right, if I replace my x with a 3, I get the sum of 3 times 3 minus 2 to the n, which equals 3, because 3 minus 2 is 1, 1 to the n is just 1. So I get the sum of 3. The limit as n approaches infinity of 3 is 3, which is certainly not 0. And so again, this guy diverges by nth term. Since both of our endpoints diverged, our series does not converge at either of those. So our interval of convergence is the open interval from 1 to 3. Does not include the endpoints because both endpoints diverged. All right, let's try another one. All right, so we're going to do x to the n over n. Again, we're going to start with the ratio test. So we get x to the n plus 1 over n plus 1. I'm going to go ahead and flip and multiply right off the bat. So n over x to the n. I'm hoping now that you guys will kind of see what cancels using ratio test. So x to the n plus 1 over x to the n, that just goes down to x. So we have xn over n plus 1. When you're doing your limit as n approaches infinity, think of x as just like a constant. Like when you're doing your limit, the thing that's changing is the n. So as n approaches infinity, n over n plus 1, that just goes to 1. And so what you're left with is just absolute value of x. And remember, for the ratio test, for this to converge, this has to be less than 1. So our radius is 1. So now to write our interval, so we write, remember it's just -1 less than x less than 1. So put it in the middle, change the sign. There's nothing to subtract or add to all three terms, so you're just done. That's your open interval of convergence, but we do have to test the endpoints. So I'm going to even write here test endpoints so that you know that's what I'm doing. So if x is -1, oh, we're starting at 0. Sorry, I think the last one we're starting at 0 too, but that's the way it goes. So we have -1 to the n over n. This is an alternating series. The limit as n approaches infinity of 1 over n equals 0. Therefore, this converges by alternating series test. If we do, 1 over n, we can just say this diverges by either p series or harmonic. So our final interval of convergence for this one so the series converged at -1, diverged at 1. So our interval would be -1 to 1, closed on -1 and open on 1. One more. So find the radius and interval of convergence. So let's do our ratio test. When you do the ratio test, I put a little note to the side here. You're doing everything in absolute value, so you don't have to worry about the -1 to the n because it's going to go away with the absolute value. So you're left with x to the 2 times n plus 1 over 2 times n plus 1 times 2n plus 1 over x to the 2n plus 1. So x to the 2n plus 1, when we clean that up, we get x to the 2n plus 3 over 2n plus 3 times 2n plus 1 over x to the 2n plus 1. So x to the 2n plus 3, that's the same thing as x to the 2n plus 1 times x squared. Because remember, when you're multiplying, you add your exponents. So this is x to the 2n plus 1 times x squared. So the next step in our limit, the x to the 2n plus 1s would cancel. And we're left with x squared times 2n plus 1 over 2n plus 3. Since 2n plus 1 over 2n plus 3, the limit as n approaches infinity would be 2 over 2, which is just 1. So you're actually left with just the absolute value of x squared. Now, if the absolute value of x squared is less than 1, absolute x squared is always positive, right, or 0. So you can drop the absolute value and just get x squared is less than 1. If x squared is less than 1, this is actually, there's a whole way of solving a quadratic inequality that I don't want to get into. Just think about it for a moment. And believe me, that means that x is between -1 and 1 again. Now, this doesn't mean the radius is always 1. It just happens to be for all of these. So Little caution though, you can't just take the square root of both sides. There is a way to solve the quadratic inequality, but right now, and really it involves a sign line, but take my word for it, it's -1 to 1. And we can talk more about this next week. All right, so our radius is 1. Our open interval, once again, is -1 to 1. So let's go ahead and test our endpoints. I am going to actually see if I can. Let's see. Group. Make all of this just a bit smaller. Oh, I made the whole thing smaller. Okay. Let's move this over. Okay. Just to give me a little more space so I can see the problem while I am testing the endpoints. All right, so our first endpoint equals 0 to infinity. First endpoint's -1. So you get -1 to the n times -1 to the 2n plus 1 over 2n plus 1. So if we clean up our negatives, you get -1 to the 3n plus 1 over 2n plus 1. Now, let's just make sure this is alternating. So at n equals 0, I get -1 to the first. At n equals 1, I get -1 to the fourth. At n equals 2, I get -1 to the seventh. At n equals 3, I get -1 to the 10th. And it's just going to keep alternating odd, even. So it is an alternating series. And therefore, we can use the alternating series test. So the limit as n approaches infinity of 1 over 2n plus 1 equals 0. Therefore, converges by alternating series. Okay, if we test the other endpoint, so we're testing 1, so we have -1 to the n times 1 to the 2n plus 1, which is just 1, right? Over 2n plus 1, another alternating series. We've already done this. The limit as n approaches infinity of 1 over 2n plus 1 equals 0. Therefore, converges by alternating, I think my handwriting is getting worse as the lesson progresses, alternating series. So both endpoints converge, which means our interval of convergence is the closed interval from -1 to 1. One last little page. Oh, shoot, the answers are showing right there. Well, that's okay. So now we know the answer going in. A couple of multiple choice problems. So for what values does this series converge? And for what values does this series converge? So for this guy, if we do a very quick ratio test, so we get x minus 1 to the n plus 1 over n plus 1 times n over x minus 1 to the n. So the x minus 1 to the n's cancel. You're just left with x minus 1 on top times n over n plus 1. N over n plus 1 goes to 1. So you're just left with the absolute x minus 1 less than 1. So once again, we have -1 less than x minus 1 less than 1. Add 1 to all three sides. So that's our open interval of convergence. This is multiple choice, so I'm not going to sit here and justify everything, but if we plug in a 0 in for our x right here, we get -1 to the n over n, which is going to converge by alternating series. So I'm just going to put an equals there. If I plug in a 2 for my x, I get 1 over n, which diverges by p-series or harmonic. So our final answer would be this guy. Last problem of the day. We're going to do the limit using our ratio test, which we're going to learn to just love, over n plus 1 times 3 to the n plus 1 times n times 3 to the n over x minus 2 to the n. All right. So x minus 2 to the n's cancel. You're left with an x minus 2 on top. There's an n on top. And then 3 to the n cancels. So let's see. We're left with an n plus 1 on the bottom and a 3 on the bottom. Okay. N over n plus 1 as n approaches infinity goes to 1. So this limit is x minus 2 over 3. And again, for the ratio test, for this to converge, it has to be less than 1. For the first time ever, we're going to have a radius that's not 1. Because remember, the radius, you need x minus a less than r, not x minus a over 3. So we're going to multiply both sides by 3. And our radius is 3. Da, 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 da. All right, so our interval, -3 less than x minus 2 less than 3. Add 2 to all three sides. -1 less than x less than 5. So now we got to test our endpoints. So at -1, you know what? I might want to rewrite this. So let me just make this a little bit bigger. So at -1, you get the series -3 to the n over n times 3 to the n. But that's the same thing, forgive me for not writing the limits, but that's the same thing as -1 to the n times 3 to the n over n times 3 to the n. Cancel, cancel. So you're left with a series -1 over n, which converges by alternating series test. So this first one converges. If you plug in x equals 5, you get the sum of 3 to the n over n times 3 to the n. 3 to the n's cancel. You're left with the sum of 1 over n, which diverges by harmonic, and therefore our answer is E. Hopefully you have enough information in your tool bag now to be able to do all of your homework, find all these radii and intervals of convergence. And on Monday, we look forward to seeing you, and I will clarify any questions and we'll go a little bit deeper. Have a great day.